Okay, good morning, everyone. And today, since we have done some basic things on um, coherence and two beam interferometry, let's now talk about multiple beam interference. It's, this will refer especially to something called Fabry-Pro interferometer, and there are very interesting applications of multiple beam interference in coatings, multi-layer coatings, and interference filters and things like that. Okay, let's start with what it is. Okay, here multiple beam interference in this case we don't produce many beams, but it is done with two optically flat identical semi-reflecting plates, or in other words semi-reflecting mirrors. Here we have two plates. One of them is here and the other one is here. And your input is from this one. Okay, that's your input. The light going in. Okay, you know what happens when light goes in like this. Okay, I haven't drawn a reflection here, but it may reflect a little bit here. But the rest will go through. Then it goes to the second plate. Some of it will go through or transmit. The other, a fraction of it will reflect. And this will continue until it exits at some point. It depends on the dimensions of the two plates. Okay, now we have to quantify it. Okay. What I'm going to do is we will take E0 as the input electric field amplitude for the wave, for the waves going in. Then both of these plates are identical with reflectance R and transmittance T. Okay, these are identical plates. Okay, now we should have just for those who haven't thought about R and T are fractions. The maximum value it can take is 1, because when R is equal to 1, it's completely reflected. R is equal T equal to 1 means it's completely transmitted. That means it's a value that's between 0 and 1. Okay. And the transmitted electric field here is RT0, and when it comes to this point, it's again transmitted. That means T square, T into T, that is T square E0. Then E0 T was something that was coming into this plate here, and that when that is reflected, a fraction is reflected, that's R here, and that continues. Here something goes out through here, and this is you have to sit and look into it. What we are interested is in the transmitted light. This is R is coefficient of reflection, T is coefficient of transmission, E0 is the amplitude, and we assume there is no absorption. So you can consider the absorption towards the end, but for now we consider there is no absorption. What we are interested is in the field distribution here, as the waves or as the multiple waves transmit through the two sets of plates. These two plates, plate 1, plate 2, as I said, they are perfectly parallel. We assume they are perfectly parallel. We don't consider any deviation from parallelism, and also we assume that it's perfectly flat. Flatness, in the case of optical radiation, it is usually considered in the order of wavelength. Sometimes if it's not a very flat, optically flat thing, and you can talk about 10 lambda as the flatness. But that's not useful for us. What we are looking at is something like lambda by 20. Here lambda is the optical wavelength, let's say 500 nanometers, and lambda by 20 to about lambda by 100. Extremely flat optical surfaces. That is necessary for this type of interference to occur. And from the figure, you could see that E0T, E0TR, E0TR square, and these are the amplitudes of successive internally reflected rays, these internal reflections, and then the amplitudes of successive transmitted rays are these ones. Now, obviously these waves are going to interfere, and there is going to be an intensity redistribution on the transmitted wave. And there are some very interesting results. Geometrical path difference between two successive transmitted rays. Okay, if you simply make, okay, this was the situation that we have explained, light going in, and the geometrical path difference. Okay, it is basically between this wave and this wave is going to be this AB plus BC is the geometrical path difference between these two waves. Okay, let's say 1 and 2. The path difference is AB plus BC. How do we find AB and BC? It's basic trigonometry. If theta is the angle of incidence, then and also you may have noticed that we don't consider the refraction at the planes or Snell's law. Just assume that these are tiny reflections. Still, the rays are going to be parallel, and the theory is not going to change much even if we include the Snell's law. Now, from triangle BCD, this is this triangle here, and the triangle ABC are used, and some trigonometric arguments. And this, if you do, BC is d by cos theta. BC is this one, this diagonal here, and that will be d by cos theta, where d is the separation. And similarly, AB is BC cos 2 theta. And if you do that, 1 plus cos 2 theta is 2 cos square theta, and that is the path difference is 2d cos theta. And associated with that, there will be a phase difference. How do you find phase difference? That is 2 pi by lambda. Because lambda corresponds to a phase difference of 2 pi, and 2 pi by lambda will be unit phase difference for a unit path difference, and this is, and also we have included the refractive index of the medium between the two planes, and this is how it's going to look. 4 pi by lambda 0 n d cos theta. The lambda 0 is the vacuum wavelength, n is the refractive index. Now we can try to sum the amplitudes of the transmitted waves. Okay, this is the first, and the second one will have a phase difference of e to the power phase difference of delta, and therefore we have included the factor e to the power I delta. Then the next one will have e to the power I delta square, then and so on. And if you do this, E0 t square is taken out as a common factor, and this is a geometrical series with r square e to the power I delta, which is like 1 plus x square plus etc. And that is 1 by 1 over 1 minus x, and therefore this is your sum. The transmitted electric field is this. Now you know the intensity. Intensity is the square of the amplitude, and therefore this will be I0 times I0 is E0 square. Okay, this basically we have to square this one, and we get something like this one. Here we have used capital T as T square, and for R square we have used capital R, and also we have replaced delta with capital delta, which is sum of that small delta and delta R, that is the small the phase change due to reflection. And if you just try to see what the magnitude of that delta R is going to be, this is for a dielectric it's either 0 or pi, it depends on the situation, and for metal coatings on the surface it can be anyway. One thing which I haven't mentioned when I explain this one is these are mirrors, partial mirrors. These two plates 1 and 2 are partial mirrors, which means they have a coating on it. It can be either metallic coating or it can be dielectric coating. And the phase change that we are now talking about here can take a random value if you are using metal and dielectric. It's either 0 or pi. And in that case, 1 minus r, okay, let's just find out what this value is, the denominator, and that is 1 minus, the modulus square is the product of the complex conjugate, and this is what you get if you do that multiplication. But cos theta, cos theta is 1 minus sine square theta, and that is theta by 2. 1 minus 2 sine square theta, sorry. 1 minus 2 cos square theta, sine square theta by 2, and that's what we have used here. Then if you do this simplification, 1 plus r square minus 2r plus 4r sine square delta by 2, and if we want to make it in a familiar form or traditional form for the function, you will see that later on. 1 minus r square is taken out because this is 1 minus r square, and therefore this is what you get. It, you substitute it on this equation here, what you will get is it is equal to I0 t square divided by 1 minus r square times 1 over 1 plus f sine square, where I have used an abbreviation f for this quantity, or This is f. And the whole thing here is called an Airy function. Airy function, you may know that it's a very famous function. And f is called the coefficient of fineness. And as the name suggests, it is a measure of how fine your resolution is, how good your resolution is, and that's why it's called it's a measure of the sharpness of the interference fringes. And that's probably the reason why it is called fineness. Fineness, okay, that is fineness. Maybe some other European language, Latin or French, don't know. Now, if you plot this Airy function, this Airy function here, this is what you get as a function of delta. It's the total phase difference. And for 2n pi, you have a maximum. 2n plus 1 pi, you have a maximum. And the difference between them is 2 pi. When the phase changes by 2 pi, you get maximum. And these are the different plots here. The green one, the yellow one, and the blue one, they are for different values of R. R changes from 0.2 to 0.9. And this resolution or the fineness goes higher as we go, as you have higher and higher reflection. How do you know that? This is your fineness. F equals 4R divided by 1 minus R square. And that is if R increases, the numerator increases and the denominator decreases, and therefore it results in a much finer spectrum represented by this blue curve. Okay, this is plotted for a single wavelength. Now, if capital delta by 2 is an integral multiple of pi, then okay, this is pi, isn't it? 2n pi minus 2n. So okay, that's delta by 2. If delta by 2 is an integral multiple of pi, or delta an integral of 2 pi, then the function is equal to its maximum value of 1. Okay. This is your maximum value, Airy function. Maximum value that can can be for an Airy function is 1 for any value of f. It doesn't matter the value of f. Or why is that? Because delta by 2 pi means the whole term here goes to 0, and therefore the intensity I transmitted will be I0 will be equal to I0 for any value of R. IT by I0 in this case becomes 1. Why did I take that? Okay, in the case of if there is no absorption, this quantity here is 1 again, because T becomes 1 minus R, and therefore this quantity if there is no absorption, otherwise it might change. Okay. Now, okay, that means for R is small, fringes broad, and indistinctive, Venus is small, and if R close to 1, it's a large Venus. What did I say? If R equal to 1, I equal to I0. Okay, that's interesting because the intensity of the bright fringes of the transmitted beams will still be there, and it will be equal to the intensity of the input beam. Because in normal case, if you are using a single mirror, to reflect light, okay, this is let's say it's a single mirror, and you try to reflect light from there, and if the reflectivity is equal to 1, because 100% is reflected, which means the transmitted intensity here will be 0. I on this side will be 0. But what I am saying here is, if when I is approximately 1, there will still be dark and bright fringes if you add another mirror under the conditions that we have mentioned before, and you will get fringes, circular fringes, and in this intensity redistribution, the bright part here will have intensity that is I equal to I0. Okay, that's you have to understand that this is an intensity redistribution. There will be very broad dark fringes there, but all the intensity, whatever intensity that is transmitted, will be concentrated on bright fringes, and that will, as R goes up and up, these fringes will become narrow. Okay. Now, let's say what the conditions for fringe maximum, and that is delta by 2 is equal to n pi, give you the fringe maximum. And if you do all this analysis, that is this is your delta is the phase, and that was for pi lambda 0 nd cos theta we have seen, plus reflection, contributions from the reflection, and that delta by 2, when it is an integral multiple of pi, we have seen that this will be there will be maximum fringes. That's 2n pi is, okay, if you rearrange things, this is what it is. Then when delta equal to 0, we get the transmitted maximum value for the transmitted intensity. When delta equal to pi, you get minimum value for IT, and if you represent the quantities like IT max as the maximum value, IT min as the minimum value, then the maximum transmission T max will be IT max by I0, and that is given by T square over 1 minus R square, and the minimum value will be, minimum transmission will be T square divided by 1 plus R square. Okay, here it is 1 minus, this is 1 plus, that's the difference. Now, Also, we can try to include the absorption because there may be little bit of absorption uh, the actual case. Therefore, if R is the absorbance, R is the reflectance, T is the transmittance, uh, the maximum intensity for A equal to 0, there is no absorption means uh, this is T square 1 minus R square is 1 because T is 1 minus R. Now the peak, okay, this is something what I told you just now. Peak intensity of the transmitted fringes will be equal to the intensity of the incident light even if R is very close to 1. And in practice, the maximum transmission will be, instead of having T square by 1 minus R square, it is uh, 1 minus A minus R. T becomes 1 minus A minus R. That is okay. If the coefficient of reflections are different, instead of taking a common R, if they are R1 and R2, then T will be T1, T2 and T2 and R1, R2, and therefore delta R is the average of delta 1 and delta 2. If the coatings are different. And these maybe it's better to keep these equations in mind because if you are asked to solve a problem, you should understand that these are the values that you need to take instead of taking one value. And that is about multiple beam interference. Now we will move to the devices that uses the principle of multiple beam interference.